Okay, now I started, when it first comes on, it's recording, then you got to turn it off, and then you forget to turn it back on. Okay, we didn't miss much. A lot of this is housekeeping stuff. I'll skip that. I'm skipping all the black blue stuff. We already talked about that. Okay, so we didn't miss much. Thank you, Eric. We're sorry for those at home. I'm recording here. I went by some stuff we didn't record. All right, so this is, we talked about this a couple times ago, the idea of a trio. And then if you expand that on out, yesterday we talked about you could take the solo, the duet, the trio, the quartet, and if you wanted to add a quintet to it, you could. We did that yesterday. And this is all of your movement throughout the day. Hopefully you don't get into quintets. That means a car wreck. That means something. That means like a particle collider or something. That's a good question you could ask particle physicists. I need to ask a particle physicist. Do those particles, and those are like proton packs, do those proton packs in a Large Hadron Collider, do they experience a quintet? I guarantee they do, but do they go beyond that? Do they go, because the speed, it's not only are those they're called particle accelerators. I don't know, they use electromagnetics, so it may not. It's like you'd have to continue to, but they do that. They step it up. So they may experience particles in a particle accelerator may experience quintets or beyond. All right. If your parents are into quantum physics, you want to ask them. All right. So then yesterday we answered these questions, and that is, that's on the screenshots from yesterday. Now, today, so we're going to do the two main things we're going to do today is we're going to do 14 and 15, and then that'll lead us back to some patterns, and then 14, 15, and 16, and then we're going to, that's my FERPA reminder so I don't show faces. I'll show you a little video on finger dancing that I took yesterday, and then I will show you some video that goes with this. This is the lab we did. We'll talk about that more later. Okay. So here we are on 14 and 15. Now, these are vectors. Remember, acceleration is a vector. It's really represented by an arrow. It's not a scalar. Velocity is a vector. Okay. Displacement is a vector. Position's not a vector, but because the position's a point. But from the origin to the position, that arrow, that's a vector, that's displacement. The length of that displacement is distance. Okay, so distance is not a vector, it's simply a length. Speed is not a vector, it's simply the magnitude of velocity. Velocity is the $50 word, speed's the $5 word. And acceleration doesn't have another term, it's just called acceleration. Okay, so these are vectors, how vectors are growing. And by the way, all of these, I don't know if I made this clear today in class, but all of these, all right, I won't mess it up yet. All three of these here, they go together. That's all one thing happening. I think somebody was thinking this is three different things happening. It's all the same thing happening. This is like if I could turn it on its side. I can't do that. It messes everything else up. Anyway, so if you turn your paper sideways and look at it from 90 degrees, it is a trio. It's just like this, okay? It's this trio, but it's on its side. And so like okay, for instance, like in the trio, I showed this in class. In the trio, I could say those are all acceleration vectors. These are four of my velocity vectors because it's growing. I'm going to say this tomorrow in class. Should have said this. These are growing. These aren't growing at all. These vectors are growing linearly with time. Velocity is increasing linearly with time, but position is changing parabolically with time. So these arrows, so that's what I've done here. Maybe I should have kept it vertical, but probably didn't have the room on the page or something. So Oh, it's on the same page. Okay, just go over here. So here I have it sideways. Okay, so if I connect the tips, if I connect the, say these, say for instance, acceleration on 14, if I connect the tips of these arrows, and I do this in a dash, well, as long as it's different color, you don't need to go dashed. Different color. So that is showing that the acceleration vector is not growing at 3 different times. Same object, not growing at not getting any greater. So it's just, so this could be a ball rolling down an incline if you said that the beginning of the ball starts is positive. It's going that way, the down the incline is positive. This would work. So it is accelerating, and it looks like, you can look at this and say, okay, that's 0 there. So it's accelerating at 2 meters per second per second. Okay, here comes somebody to turn that test in. If you're virtual, why aren't you here? Oh well, no judgment. So that's 2 meters per, so I can plug this in for acceleration. 2 meters per second squared. Okay. Now I'm going to help you. I'm going to help you a lot on 14. Then on 15, I'm going to let you kind of try and do it by yourself at first. So we know that the next, for velocity versus time, we know that the arrows, the tips of the arrows, will all line up linearly because it's growing linearly. So I'm going to go ahead and put a blue line there, and that's my template. So if I had 3 seconds, 4 seconds, 5 seconds, it's really easy on a trio to draw the remaining velocity vectors because you just use that template, and then I draw my new arrow. I'll do my arrows in green. Okay, you see that? So that's now the velocity at 3 seconds. So we're looking at, okay, here's the deal. I made this thing up about 10 years ago because students, when we get to forces, which you're going to get to, I promise you, forces and free body diagrams and work and energy and all that, and power, we'll do that, and torque. But I'm still laying foundations because forces grow, get smaller, and they're arrows, right? Just like this. So once you learn the basics of vectors and arrows and, you know, how they change, force is simply what causes that acceleration. So every physicist through history first studies kinematics, first discovers, like Newton, like Galileo, Descartes. They all discover motion first because that's the observable, right? It's the observable, what you see, and they diagnose that motion. Now later, Galileo did not get forces. It was later that Newton came up with forces. So we're learning this stuff the way the great thinkers learned it. I'm trying to get your brains to grow in the way that theirs grew. In a nutshell, that's really what I try and do every day. I try and find a way to put you in the same situation that the great thinkers were in, and see if you grow the same dendrites. I'm trying to produce a genius. Okay. So, yeah. So here we go. So the equation, now we go over here and we go to the equation, and there's okay, we're in a trio, right? So there's the equation I'm dealing with. V is equal to AT plus V naught. So I come back here. That's why you got to have it in your head. V equals, blow this up a little bit. V equals, in general, AT, that thing's irritating. AT plus V naught. So if this is worth, say this blank here is worth 3 points, I'll give you a point for that. You got the right idea, but there's actually, we need numbers. There's really are numbers. Now, if I extend this back up here, if I extend this back, you see that this at 0 time, if I had a 0 right there, and in fact I do on tests, on the take-home test, not this one, the next one. At 0 time, I'd be at 0 velocity. So V naught is 0. You can erase that. And then A, I already know it's 2. Okay, so this is better to go ahead and fill it in. V equals 2. And you can't just say V equals T equals 2T, because that would mean unit-wise messes up. The 2 has to have units to make it work. If I say velocity equals 2 times the time, then you would say, okay, so at 10 minutes, I'm going at 20 miles per hour. It doesn't make any sense. So you have to put units to meters per second squared times t. See, when I do this unit analysis wise, the meters per second squared and then t is in seconds, one of the seconds cancels, and I'm left with meters per second. So that we'll do this exercise probably December or in January, where we're trying to figure out the units. Actually December, where we're trying to figure out the units of the constants. Okay. Now what? Now we get to this one, but the problem with this one is it's a parabola, right? So I can't use that ruler. I can't just figure out the next, and that's what students were trying to do. I said, no. We got it, but we kick it up a notch, right? So if you come back over here, that's the graph I'm dealing with now. So it's x equals kt squared. All right, x equals kt squared. Once again, this will get you some points. You want to grab all the points you can. All right, so now we look at this in particular. I need numbers here. I want to know what k is, in other words. Well, this points to 1 meter. The first vector is 1 meter long. This is 4 meters long. Okay, so from that, I should be able to find k. What do you think? You all are smarter than the average bear. What would be the next one? This is like an ACT question. What's the next? Say again.
9 meters.
Ah, you got it. You got it. There's the I'm giving you 2 assume points for that. 9 meters. See, the one who speaks up gets the points. 9 meters is the next one because it's a series of squares, right? So that's 9 meters. So if you look at the series in ACT, 1, 4, 9, everybody would know that the next one's 16. Okay, so in that case, what is k? Plug in your numbers. If t equals 1, x equals 1. If t equals 2, x equals 4. If t equals 3, x equals 9. What is k? Is the sound working? You guys' microphones off? Come on, the class got it by now. I'll wait it out. We'll sit here till 5 o'clock.
Can you repeat what you said?
Okay, I'll say it again. What is k?
K equals 1.
Thank you. You guys knew it the whole time. You're just messing with me. All right, so k equals 1. Is that it? K equals 1 what?
1 meter.
Okay, see, now think about it. It's the units got to work. So it's not a meter. Because if I plug a meter in.
Oh, second.
If I plug a second in, it still ain't gonna get it. You're on the right track though. You're thinking here. This is in terms of meters. This is in terms of seconds squared.
Meters per second squared?
There you go. There you got it. And this is an exercise we're going to do in December. Now I know I want to do it. So that must be meters per second squared. That's kind of how you figure it out. So it's not just 1, it's 1 meter per second squared. We're going to need this number in a minute. So that's important. And that goes right there. Because otherwise, if we don't put any units on there, you're saying that meters equals seconds squared. Well, that's pretty silly. Okay, it's apples and oranges. All right. So now you guys are, I'm going to give you some time to try and do 15. We can start together. The first one, remember, this is another trio, another positive trio. And these get harder because sometimes it becomes quartets. Sometimes it becomes negative. A lot of times there's initial velocity. Sometimes you're given a weird arrow to begin with. So these are puzzles. You'll see probably 4 or 5 more of these before the year's over, the semester. We don't do the second semester. All right, so the first one is it's pointing to 3, right? So in this case, acceleration is 3 meters per second squared. And remember, acceleration is the grandfather. That's the one that gives rise. This graph here gives rise to this graph, which then gives rise to this graph, right? This is the foundation. This right here is the foundation of this equation and this equation. And that, my friends, is the essence of integrals in calculus. Right there. Okay, I'm still giving you time to work on the velocity. And then the harder one is, of course, the parabola, the position. I know what I'm going to do. Oh, this is dangerous. I'm going to, while I'm giving you time.
So do you just add 4.5 every time, or?
No, because if you did that, you would have a linear function. Remember, the change is changing. For those watching this on video, the question was, how do we find K? We're working on number 15, and I gave them some time to work. So then I need to let you know this. 1 second, we're at 1.5 meters. At 2 seconds, we're at 6 meters on this number 15. And so the question that was raised is how do you know, how up here did we find that K equals 1? And we did it by looking at, first off, we know this is the foundational equation. It's x equals kt squared. That's my foundation. So I know that I've got to square the time. So at x equals 1, if I plug in 1 for t, when I plug in 1 for t, I get 1 second gives me 1 meter, just like this. When I plug in 2 for t at 2 seconds, 2 squared is 4, and that gives me 4 meters. So in other words, x is just equal to t squared. There's nothing else happening to it. It's not being multiplied by 2 after that. You know what I'm saying? It's not being multiplied by half or something. Okay. All right. So if you are working this at home, if you're still working on it, you just need to hit pause for a second. So we're about to go into the answers on 15. So let's see if you guys did this. So here, different color pencil, and I align those tips up. And that also tells me that at 0, it must be at 0, because it's, and it would have told me if there was initial velocity. And so here we have the velocity at 3 seconds, and here's the velocity at 4 seconds. Okay. So the equation is that V is equal to AT plus V naught. There is no V naught, so V is equal to AT. So the equation is pretty easy. It's simply V equals, I don't say A, I actually plug it in, 3 meters per second squared. I don't need that anymore. 3 meters per second squared times T. Okay. So we're clear there. My studio audience, we are clear so far. Okay, now we get to the hard one. This is the one that always throws students on tests. And that is, now what do? We know our general, once again, you're going to get points if you write it down. So x equals k t squared. You at least tell me you know that much. Now we just got to find k. And so it's not like last time. So I would just probably do some kind of let's come up with some kind of chart. We have x equals k times t squared. Hold on. And let's go this. First time I've tried this, but this might work. So we have, we look at our x's. Hold on. All right. X equals. Okay. So we look at our x's and we have 1.5 and 6. So I have 1.5 meters, 6 meters. And then t is 1. So t is 1. 1 squared is 1. At 2, t is 4. 4, not 2. At 2 seconds, t squared is 4. So if that's the case, to make those equal, what did I multiply t squared by?
1.5.
Exactly, 1.5. And so it works for both of those, and there's no reason why it wouldn't work for any of them. So therefore, I know that k equals 1.5. 1.5 what? What are the units?
Meters per second squared.
There we go. So it's acceleration again. And that's important. So k equals 1.5 meters per second squared times t squared. There we go. Now the rest is easy. Now that you have those first two. Now the weird thing about tests are, no, not tests, I mean take-home tests or more complicated problems is I don't give you the first two. I give you like 3 and 4, and you got to work your way back. The puzzle gets harder. I don't know if this year we'll do that, but normally the puzzle gets harder as the year goes on. We're just not giving as many tests as I usually give.
So is k always half of a? You jumped ahead of me. You answered 16. That's fantastic. Let's hold that. The answer is yes. Oh, let's go with it. Okay. Since the cat's out of the bag, k equals 1/2 a. Always in a trio. That's only in a trio, not in a quartet. So now let's go back up here. Now, since that's true, we can beef up. We can go to version 2.0 of our Rosetta Stone here. And this is extremely important, actually. Galileo would have killed to know this information. But x is not equal to kt squared. Remember, all Galileo said was x is proportional to t squared. But it was Newton that figured out later that x equals 1/2 a t squared. So, and that's always true for anything. It could be you in your car. It could be a ball rolling down a ramp. It could be a asteroid falling from the sky. Now, I can't, not like a leaf. I mean, because a leaf has got a huge amount of air drag, which you'll get to more next semester, and all those other forces involved. But in free fall, this is how things fall to the ground. I mean, it's pretty important considering any kind of sport. This equation is involved in a free throw, in a three-pointer in basketball, in a spiral in football. All of those involve this equation in one form or another. What? Hold on. I'm about out of juice. That was weird. Ugh, I need a laptop. Okay, so yeah. Oh, now watch. Check this out. Now let's do it down here for this one, for a quartet. Remember the blue. The blue tells me that what happens in a trio on that diagonal, the same thing happens in a quartet. So what is this? See, okay, so he got busted. He's coming over to, he's bringing me his stuff, but he's not at our session. Oh well. Here comes two people. All right, so V equals what T squared?
1/2 J.
What the? You can't be that fast. V equals 1/2 J T squared. That's worth probably 2. Cleaning up on Zoom points today. Early bird, man. You got to have your finger on that mic. 1/2 JT squared. So all you do is, I thought you were going to say, 1/2 A, because that's what they'd say in class, a lot of them at first. They were trying to apply but the rule is you go 2 below. You go, get this guy. What is this guy doing? You go 2 below and grab this one and bring it up. So here you go 2 below, that's jerk, bring it up. And it turns out that is what happens in a jerk situation to velocity. Now, then someone said, well, can we also apply that to here? No. I'll go ahead and tell you what I told third hour. I guess if I told them, I can tell you. And that is, they persisted, wanted to understand, well, what is that? So that right there actually ends up being, this isn't gonna make any sense. This isn't gonna make any sense right now. But that actually ends up being 1/6 J, not J brute, 1/6 J. See, it all emanates from the J, and you go, well, why 1/6? And the answer, my friend, is calculus, is integrals, and something called antiderivatives. But that's a coming. That's a coming. Okay. I mean, the history of physics is sort of the history of math as well. It's the history of the cool math, not the math. These fractals are cool and all, but come on. I mean, and they do have some practical experiments. Okay, so now let's go backwards now. Let's go ahead and get these last 2 vectors. Now that we know the equation, we can easily plug in. 3 squared is 9. 9 times 1/2 is 13. So now we can draw the next 2 just for completeness sake.
It's 13.5.
13.5, thank you. 13, well, yeah. Best I can do here is probably guesstimate 13.5. And then the next one, of course, it's 16, and 16 is going to be 24. And there you go. Now we connect our tips, and they should connect in a parabola. So I'll do my best shot here. 0, 0, we assume that. And then, hold on. Here we go. Sometimes this is iPads. I'm lefty. For lefties, iPads are not made for lefties. I wrote them a sternly worded email. Actually, it's not the iPad's fault. It's this Eventbrite. It's this what's it called? Explain everything. All right, so there is the parabola. Sure enough, it looks like a parabola. Okay, that officially ends, finally, this extremely long and that's probably the hardest worksheet we've had so far this year. And you could almost write a whole test off that one worksheet. But it's not going to be next week, okay? This is not on next week's test. I want plenty of time for it to kind of ferment in your brain. Let's let this ferment over Thanksgiving, and then I'll test you on it. Okay, so now I put the FERPA there because I can't show you. Well, I can show you, but I got to stop recording. When I can do the finger dance because that's just a finger. I want to show you this. Let me share into the screen. Share screen. I want to share. What do I want to share? I want to share. Screens are up here. I want to share. Oh, this. Okay. So let's go to photos. You see my photos there? These are actually videos. Everybody see those? Okay. Here's the finger dance. And this is what you can do. You can do this. You can do a video like this. I'll start it and then I'll explain. Okay, this is Finger Dance Fall 2020.
Ready, and 1, 2, 3, 4.
Okay, now what the bejeebers is she doing? Well, that's okay. So she has to show me a 20-second dance, and the dance choreography is on the back of, I think it's 2.4. I think, yeah, I think it's 2.4. And you all were supposed to choose group 7 for your choreography. And you go along and you put these Post-it notes. This is a student invention over the years. They put Post-it notes, now it's required, every second. So we know where the finger is. So we know, so you know, when you're doing the dance, and otherwise people get nervous. I'm watching them, I taunt them while they do it. No, I don't, I'm not taunting. But everybody's watching. So you get your brain, serotonin. So not the cortisol. So you put a sticky note every second so that you know where your finger is every second. That's what she's doing. So most of the work comes in the finger dance is before the actual dance. Once you're dancing, it's easy.
5, 6, 7, 8, 9.
No, see, she turned around. She turned around because the choreographer told her to. The choreography, the graph, the V versus T step function told her to turn around and go backwards for a little bit.
9, 10, 11.
See, she's going faster here essentially because she's covering more space with every second.
12, 13.
Now she turns around again.
14, 15, 16, 17, 18, 19, 20. Woo!
Okay, so that's an example of finger dance. And I'll give you they got 25 points for that. They came in on their own on lunch. So I thought, and only 2 groups have done it. So I'm kind of giving away the points here, folks. So if you're needing points, I'm also extending the deadline till the Sunday after Thanksgiving. Okay, so maybe over Thanksgiving you're bored out of your mind, then do a finger dance. Or if you want more points, perhaps you go a little more creative. Okay, you do a dance, or I had a girl do a ballet once, and they do Swan River, and they make little stories up. I mean, they put disco on. So all of that is cool. It's sort of like what do you call it? Vine. It's not Vine, but it's that Chinese thing, TikTok. So you can make your own finger dance TikTok. Nobody would understand it, but it'd become the national rage, the national sensation, and all of a sudden everybody's doing finger dances. I'm just saying that could happen. Okay, now let me show you, and I'm going to turn this. Let me turn this off. I'm going to pause it. Well, I won't pause it first. I want the audience to get a feel for what we're doing here. All right, so now I want to look at what happened in the hallway today, because that's going to explain what's going on here. We're almost done. We're getting closer. Okay, so I took a couple of videos in the hallway, second hour. Here we go. You see it okay? Yep. So what we're doing is this is something I made up this summer. We're rolling a ball up a ramp, and then it's coming back down. And this is called the perfect bow tie. Remember I said it's like a baseball, like a basketball? Well, the thing is, baseballs, basketballs, footballs, they don't just come down. They go up first, then they come down. So we need to understand the whole motion. And so we're trying to understand projectile motion. All right, ballistics eventually. It's going to teach, this is going to lead us to ballistics. Okay. In astronomy, things like that. So the ball goes up the ramp. We put a little cup on the end, and that gave us a 3-degree angle. So we took our phones out, and you can measure angles, So we measured about a 3-degree angle on that. So everyone had the same thing. So here it looks like Bennett. He's got to let the ball go. It's got to hit up. Oh, I can't cursor. It's got to hit up here, right up in here, and then roll back down. So it's hard to do because he has to get between 2 little points here. All right.
That's close. That's close, though.
Hey, you know what? I may have a legal way out of this FERPA thing. People are wearing masks. It's almost like they have masks on. I need to get, that's what I got to do. Okay, everybody's wearing masks. I've got to get eye masks, when I'm videotaping the class, we got to put on Mardi Gras. I got to buy like 20 Mardi Gras masks. Okay, or maybe masks like Batman or something. I'll order those. That's pretty cool. That'd be a good idea. Then I can film anything I want. Okay, so that's what all the groups did. Okay, they're all rolling in. Then they do that. You finally get it to work once, and then you have a timer, you have a spotter, and you have a pusher, the one that pushes the marble up the ramp. Okay, and let's see. All right, so you got to feel. I'm going to stop there. I don't want to get too close to people, and so you might recognize them, I guess. But that's what we did up and down the hall in class today. Okay, so, and I'm still recording. Yes. All right. Okay. So now I'm going to share the other screen now, and we'll wrap this thing up. We're almost done. We're about 5 minutes away from being done. I always feel like I should apologize to you guys, but you guys can always just leave. You don't have to. It's not, if you check out, it's not rude. You just got to go. You don't need to say, hey, I got to go. Just go. Or you can jump in. Students say, well, it started at 4. I don't care if you jump in at 4:30. Jump in for 5 minutes and get out. That's fine. Now, if I just get out, that'd be rude. All right, so call a perfect bow tie, and all we got done, we came back in class and we filled this table in. All right, so let's put in the numbers from us. Let's put the numbers in from today. The average overall tau, the overall time was 6.6 seconds. Now that's the overall tau. This is called half tau. That's how you say it, half tau. And so they'll say, like in projectile motion, they'll say, well, what's your half tau? That's your time to get, it's a perfect bow tie. We're assuming there's little, if any, air drag. All right. Air drag's a whole different ballgame. We've touched on air drag in one of our gold standards, but you use that formula. So what is the time to the apex in this case? What do you say?
Would it just be 3.3?
Exactly. We assume that it's symmetrical. Symmetry is a huge concept in physics. We use it all the time. They use it all the time in quantum. They use it all the time in advanced chemistry. What is the delta X to the apex? Now, we said that the ball always it was supposed to leave the ruler at 25 centimeters. And then it went, I'm guessing, about 225 centimeter mark. So overall, it was 225 centimeters minus 25 centimeters. So for the virtual class, we're going to say 200 centimeters. Nice, even round number. And then finally, for today, I'll give you one more thing, but what's the velocity at the apex? What would the velocity be? Like if I throw a ball in the air right now and it hits the apex, remember the apex is the highest it can get. What would be the velocity at anything's apex?
Can you just go ahead?
Oh, I just had 9.81.
The acceleration due to gravity is 9.81, but I want to know what the velocity is at the apex.
Do you just do 200 divided by 6.6?
What that would give me would be average. Actually, that'd be wrong because the 200. Well, more like 200 divided by 3.3, right? Because that's 6. Okay, this is something from geophysics. That's 6.6. I should have brought this up in class. That 6.6 is called two-way time.
but if we're going to do a find a velocity, that 3.3 is what we need. We need the one-way time. And it's something we do in geophysics all the time. We blow dynamite in the earth and the signal goes down, and there's two-way times and one-way time. Okay, so what is the velocity at the apex? What is the velocity of anything at the apex? Remember, apex. Okay, so apex. Apex is the highest point that if I throw a baseball in the air or my phone in the air, whatever it is, if I throw it in the air, it's the highest point it achieves. So is it, say it again.
0.
0. There you go. Miranda jumped in there. I'll give her a point because she saved the day. So let us get off this Zoom. 0 centimeters per second. That's always true at an apex. That helps a lot knowing that that's true. We'll get to that more tomorrow. Okay, the last thing is we deal in three different bases of units. We deal in the CGS system, we deal in the MKS system, and we deal in the FSS system. I think we mentioned this once before. 80% of what we do in the class is in the MKS system. About 5% is what we do in the CGS system, and 15%, this is all approximations, in the FSS system. So what does MKS stand for?
Meters, kilometer. Wait, yeah, meters, kilometers, seconds.
Well, you got the meters and the seconds right. You got the
Kilograms.
kilograms, right? So you're on the right track. Meters for distance or displacement, kilometer or kilograms for mass, and seconds for time. Those are the three basic units, in physics. Well, then what does CGS stand for?
Centimeters, grams.
Right, centimeters, grams, seconds. A smaller scale, right? If you're doing more small scale things. So what do you think astronomers use?
MKS.
Yeah, that makes sense, right? No, they use CGS. And the reason is, I mean, you think astronomy, we're talking long distances. The reason is when it comes down to grinding lenses, that is really small scale. So astronomy deals with lenses all the time, right? Optics. So it makes sense that astronomy, actually does make sense astronomy use CGS. So in this, today, we're going to use CGS. Last one, what the heck does FSS stand for? We know, I'll give you the last one. The last one's seconds.
Is the F feet?
F is feet. Okay, I'm giving you a point for that. Now for 2 points, what's the middle S? Oh, you're looking it up. It's slugs. And this, boys and girls, is what the United States uses. Now, no good scientist in the United States would ever use this, but this is what we base our measurements on, the Looney Tunes method. Okay. So we do FSS sometimes because we are Americans and you got to be able to talk, turkey with people. So we'll make conversions. Okay. Now I think we are done. I have kept you up. Okay, 4:54, not so bad. Any questions?